Have you ever wondered what lies beyond the darkness between the stars? For most of human history, we believed the Milky Way was the universe, that our galaxy was everything, that the night sky above us marked the edge of existence itself. But that comforting illusion would not survive the truth. Tonight, we journey into the untold truth about trillions of galaxies. 2 hours of space stories meant to carry you gently into sleep while revealing the vast ocean of worlds we once mistook for emptiness. When you look up at the night sky, you are not seeing the universe as it is. You are seeing its past, a moving archive of ancient light. Every faint glow carries a fragment of the cosmos, billions of years old. And hidden among those whispers are galaxies, countless galaxies, each one a spark in an ocean too vast for the human mind to grasp. For centuries, astronomers charted the heavens, believing we stood at the center of creation. Then came the doubt, the telescopes, the discovery that changed everything. Those faint smudges in the darkness were not clouds of gas within our galaxy. They were entire universes of their own, islands of billions of stars stretching across distances that swallow human comprehension. Now, with instruments like the James Webb Space Telescope, we peer deeper than ever before. We see galaxies forming when the universe was only a breath old. We watch stars being born in the cosmic dawn. We trace the very atoms in our bodies back to those ancient furnaces of creation. Every observation is an act of time travel, a way of touching the universe not as it is, but as it once was. If you enjoyed this journey through the cosmos, consider subscribing and leaving a like to help others find their way to these stories. Let the weight of the day drift away as we explore the infinite together. Welcome to Sleepy Science Stories. The night sky we know is a portrait painted in time. When you look at a star 10 light years away, you are seeing it as it appeared 10 years ago. When you observe a star 100 light years distant, you are witnessing its past from a century ago. The light from these stars departed their surfaces long before it reached your eyes, traveling through the void at the fastest speed physics allows. Nothing in the universe can move faster than light, and yet light itself takes time to cross even the smallest cosmic distances. This creates a strange paradox. The universe we observe is not the universe that exists in this moment. It is a tapestry woven from different moments, different eras, all arriving at our eyes simultaneously, but originating from vastly different times. Think about that for a moment. Every star you have ever seen with your naked eye, every constellation that guided ancient sailors, every point of light that inspired poets and philosophers, all of them belong to our local neighborhood. They are our immediate cosmic family. The nearest stars are merely 4 light years away, while the farthest visible stars sit perhaps a few thousand light years distant. In the grand scheme of the universe, these distances are negligible, like measuring the space between houses on a single street while ignoring the existence of entire continents beyond. The true universe, the full expanse of existence, stretches thousands of times farther than anything our unaided senses can perceive. We live inside a galaxy, looking outward through a fog of stars, unable to see past our own local veil without the aid of instruments that can pierce that curtain. For most of human history, we believed this local view was complete. The visible stars were assumed to comprise the entirety of creation. Ancient astronomers catalogued thousands of stars, noting their positions and movements with remarkable precision. They divided the sky into constellations, mapped the wandering paths of planets, and recorded eclipses and comets. Yet despite this careful attention, they remained unaware that their observations captured only the tiniest fraction of what exists. The visible stars represent perhaps 1/10,000th of the stars in our galaxy alone. And our galaxy, as we would eventually discover, is itself one among countless trillions. The ancients were mapping a single room, while remaining oblivious to the vast mansion that surrounded them. On the surface, it appears to be a question with a straightforward answer. Tally the galaxies, sum them together, and you understand the vastness of existence. But the answer conceals itself in the fundamental nature of light. We can perceive only what has found its way to us, and light moves at a limited velocity. Each observation becomes a glimpse backward through time, not a present image, but an echo. To determine how many galaxies populate space, astronomers must gaze across billions of years into ages where light has been pulled thin, dimmed, and nearly erased by the expanding weave of space-time. Even with our most powerful instruments, the endeavor borders on the impossible. A galaxy is not a permanent fixture. It transforms, crashes into neighbors, and dims. Some disappeared before their radiation could ever find us. Others shine so faintly that no device on our planet can register them. What we catalogue are phantoms of yesterday, not the breathing cosmos as it stands in this moment. And yet, from these delicate threads of primordial light, astronomers attempt to assemble the unthinkable. A complete inventory of the universe, knowing perfectly well that most of it will stay eternally beyond our reach. The challenge is not merely technical, but conceptual. When we ask how many galaxies exist, we must specify when. The number of galaxies in the early universe was different from the number today. Small galaxies merged into larger ones. Some galaxies fell into black holes. Others formed from collapsing gas clouds. The population of galaxies has evolved throughout cosmic history, constantly changing. So when we count galaxies, are we counting them as they existed when their light left them, or are we trying to estimate how many exist right now, in this present moment across the universe? These are different questions with different answers. And because we can never see the present state of distant galaxies, only their past, the second question may be fundamentally unanswerable. Consider the peculiar nature of cosmic observation. When a photographer captures an image of their family, everyone in the picture exists in the same moment, frozen together in time. But when an astronomer photographs the universe, each galaxy in the frame exists in a different era. The nearest might be seen as it was a few million years ago. Another, farther back, appears as it was, 500 million years in the past. The most distant shimmer in the corner of the image shows a galaxy from when the universe was merely a child, less than 1 billion years old. A single photograph of deep space is not a snapshot. It is a timeline, a historical record spread across billions of years, with each object representing a different chapter in the cosmic story. This makes counting galaxies not just difficult, but philosophically complex. Are we counting galaxies as they exist now, or as they existed when their light began its journey? The question itself reveals the strange relationship between space and time, the way distance and history become inseparable at cosmic scales. This temporal confusion extends to everything we observe. When astronomers study the properties of distant galaxies, measuring their masses, their star formation rates, their chemical compositions, they are studying ancient properties, not current ones. A galaxy observed with a redshift of 5, appearing as it was when the universe was roughly 1 billion years old, has had 12 billion years to evolve since its light began traveling toward us. In those 12 billion years, that galaxy has likely merged with others, formed new generations of stars, perhaps even developed spiral arms, or settled into a mature elliptical form. We are seeing its baby picture while it now exists as an elder. This disconnect between observation and reality is one of the fundamental challenges of cosmology. Each evening, the heavens appear boundless, yet what reaches our eyes is merely a sliver of what truly exists. The stars that glitter overhead are primarily close companions, residents of a slender galactic plane, no wider than a few thousand light years. Past that curtain, the universe expands hundreds of billions of times farther still. Our unaided vision cannot detect galaxies. It can only perceive the most luminous corners of our own. For observers in ancient times, that threshold felt absolute. The starlit void was the divide between what could be known and what could not. But the emptiness separating those stars is far from barren. It overflows with light too weak for human perception, radiation so ancient it has been transformed into invisible frequencies. When astronomers eventually pointed their instruments into these shadowed regions, they did not discover absence, they uncovered abundance. Thousands of galaxies appearing where once there had seemed to be nothing. The peaceful darkness hovering above us was never the boundary of creation. It was simply the shoreline of an endless sea we had mistaken for the horizon. The darkness of the night sky itself is a puzzle known as Olber's paradox. If the universe were infinite and filled uniformly with stars, then every line of sight from Earth should eventually intersect a star. The entire sky should blaze with the combined light of infinite stars, as bright as the surface of the sun in every direction. Yet the sky is dark. Why? The answer involves both the finite age of the universe and its expansion. Light from the most distant stars has not had time to reach us yet, and light from extremely distant sources has been redshifted so much by cosmic expansion that it becomes invisible, its energy diluted across expanding space. The darkness we see is not emptiness, but rather a combination of distance, time, and the fundamental expansion of space-time itself. In a sense, the dark night sky is proof that the universe had a beginning and has been expanding ever since. Our eyes evolved under the light of a single star, our Sunday. They developed to detect the specific wavelengths that reach Earth's surface, the rainbow of colors we call visible light. But visible light represents only a tiny fraction of the electromagnetic spectrum. Beyond the red edge of what we can see lies the infrared, a realm of longer wavelengths that carry heat and ancient starlight. Beyond the violet edge lies the ultraviolet, and farther still, X-rays and gamma rays. Each of these invisible forms of light tells a different story about the cosmos. When we limit ourselves to visible light alone, we see only a fraction of the universe's activity. Stars emit most of their energy in the visible spectrum, which is why we can see them. But galaxies billions of light years away have had their visible light stretched by cosmic expansion into the infrared, rendering them invisible to eyes that evolved to see only the light of our nearby Sunday. To truly see the universe, we needed to build eyes that could perceive these invisible wavelengths, instruments that could translate what is hidden into forms we could understand. The electromagnetic spectrum is vast. Radio waves, with wavelengths measured in meters, reveal cold gas clouds and the remnant radiation from the Big Bang itself. Microwaves show the thermal glow of dust and the cosmic microwave background. Infrared reveals cool objects, planetary atmospheres, and distant galaxies whose light has been redshifted. Visible light shows us stars and galaxies in their glory. Ultraviolet captures the hottest stars and violent processes. X-rays emerge from superheated gas and the environments around black holes. Gamma rays, the most energetic photons, signal the most extreme events in the universe: supernovae, gamma-ray bursts, matter falling into black holes. Each wavelength range requires different instruments, different techniques, different orbital positions. Some wavelengths penetrate Earth's atmosphere and can be observed from the ground. Others are absorbed by atmospheric gases and require telescopes in space. To understand the universe fully, we must observe it across the entire spectrum, assembling a complete picture from many different types of light. Before the age of modern instruments, the cosmos was an enigma sketched across the heavens. Astronomers mapped the movements of stars, followed comets, and measured the faint river of the Milky Way. Yet everything observable appeared to exist within a single contained realm. Even brilliant minds like Galileo and Herschel believed the stars constructed one enormous framework, possibly finite, possibly without end, but still belonging to us alone. The notion that each hazy cloud might represent another realm of stars was dismissed as wild conjecture, a dream beyond rational thought. Still, wonder endured. Some astronomers, gazing through their basic devices, observed that certain mists appeared unusual. Spirals, disks, or blurs too remote to understand. They argued intensely. Were these vapors inside our galaxy, or were they island universes standing on their own? For generations, no one possessed proof. Either way, the mystery lingered in observatories like a faint whisper in the void. Humanity balanced at the threshold of an enormous revelation, staring into it without comprehension. The telescopes of the 18th and 19th centuries were marvels of their time, but primitive by modern standards. They used glass lenses or metal mirrors to gather light, focusing it for human eyes to observe directly. Astronomers sat at the eyepiece for hours, sketching what they saw by hand, recording their observations in notebooks. There was no photography, no electronic detectors, no computers to process data. The human eye and brain were the only instruments available for interpreting the light from distant objects. This limitation meant that faint objects were nearly impossible to study. The eye cannot accumulate light over time the way a photograph can. What you see in a single moment is all you get. Nebulae appeared as faint smudges, their details obscured by the limits of human vision. The introduction of photography in the late 1800s transformed astronomy. Photographic plates could be exposed for hours, accumulating light gradually and revealing details invisible to the eye. Suddenly, nebulae that appeared as featureless clouds through eyepieces showed intricate spiral structures in long exposure photographs. Stars too faint to see became visible as tiny dots on photographic emulsions. The universe revealed itself to be far richer and more complex than direct visual observation had suggested. Photography became the astronomer's most powerful tool, a way to see deeper, to record data permanently, and to measure positions and brightnesses with precision impossible for the human eye alone. The debate became known as the Great Debate, a famous confrontation between two astronomers in 1920. On one side stood Harlow Shapley, who argued that the spiral nebulae were merely gas clouds within the Milky Way. On the other side stood Heber Curtis, who proposed that they were separate galaxies far beyond our own. Both men presented evidence, both made compelling arguments, but neither could deliver the decisive proof that would settle the matter. The instruments of the time were simply not powerful enough to measure the distances involved. And so, the question remained open, a cosmic mystery waiting for the right technology and the right observer to solve it. The uncertainty itself was maddening. Imagine living in a world where you could not know whether your home was a solitary island or merely one shore of a vast archipelago. That was the state of astronomy in the early 20th century, teetering on the edge of a revelation that would change everything. Shapley's argument rested on measurements of the Milky Way's size. He had used observations of variable stars in globular clusters to map the structure of our galaxy, discovering it was far larger than previously thought. If the Milky Way was so immense, he reasoned, then perhaps the spiral nebulae were small objects within it, not separate galaxies at all. Curtis countered with observations of novae, stellar explosions, in the Andromeda Nebula. These novae appeared much fainter than novae in our own galaxy, suggesting they were much farther away. He also noted that Andromeda showed a redshift in its spectrum, consistent with it moving away from us. Something expected if it were a separate galaxy in an expanding universe. But the evidence on both sides was circumstantial. What was needed was a direct measurement of distance, and that would require identifying stars in Andromeda whose true brightness was known. Knowledge often emerges not from certainty, but from uncertainty. By the closing years of the 1800s, that uncertainty had started to burn among astronomers. Why did certain nebulae seem so impossibly distant, so disconnected from our galactic disk? Why did their radiation behave unlike the stars nearby? A handful of bold thinkers began to question whether these curious spirals might exist outside the Milky Way entirely. But making such a declaration would imply something revolutionary, that the universe stretched far vaster than anyone had dared to contemplate. That fragile uncertainty became the foundation of modern cosmology. If these clouds were truly separate galaxies, then our entire understanding of reality would shatter and reform overnight. The universe would transform from a solitary island into a sea of countless worlds. Yet without evidence, the theory remained nothing more than a murmur echoing through observatory halls. For the time being, humanity still positioned itself at the heart of its own imagined cosmos, awaiting one decisive observation to shatter the fantasy forever. And so, with that single uncertainty, humanity took its first genuine stride toward infinity. The philosophical implications of this uncertainty were profound. If the spiral nebulae were indeed separate galaxies, it would mean that human existence occupied an even smaller corner of creation than previously imagined. Not only was Earth not the center of the solar system, not only was the Sun just one star among billions, but the entire Milky Way galaxy would be revealed as merely one among countless others. It was a humbling proposition that some resisted on almost emotional grounds. The idea that we are insignificant, that our entire galaxy is just one spark in an infinite sea, challenged deeply held notions about humanity's place in the cosmos. Yet the evidence, though incomplete, continued to accumulate, pointing inexorably toward a universe far grander than anyone had imagined. The universe has a way of humbling us. Throughout history, each major discovery in astronomy has displaced humanity from the center of things. First, Copernicus showed that Earth orbits the Sun, not the other way around. Then, we learned that the Sun is merely one star among hundreds of billions in our galaxy. Next would come the realization that even our galaxy is nothing special, just one of countless others scattered throughout an incomprehensibly vast cosmos. Each step outward expanded our understanding, while simultaneously diminishing our sense of cosmic importance. Yet paradoxically, each revelation also deepened our connection to the universe. We are not separate from this vastness. We are made of it, assembled from the same matter, governed by the same forces, participants in the same unfolding story. To discover our insignificance is also to discover our kinship with everything that exists. This pattern of displacement, sometimes called the Copernican principle, suggests that we should not assume we occupy any special or privileged position in the universe. Wherever we look, we should expect to find conditions similar to those around us. There should be nothing unique about our location in space or time. This principle has guided much of modern cosmology, leading to predictions that have been confirmed by observation. For instance, if we occupy no special position, then observers in distant galaxies should see roughly the same distribution of galaxies around them as we see around us. The universe should look roughly the same in all directions and at all locations, a property called homogeneity and isotropy. Observations of the cosmic microwave background and the distribution of galaxies confirm this. The universe, at the largest scales, appears remarkably uniform, with no special center, no preferred direction, no indication that any location is fundamentally different from any other. Every telescope functions as a time machine. The deeper we observe, the more ancient the universe reveals itself to be. when astronomers capture the subtle glow of faraway galaxies, they are not viewing them as they appear today, but as they existed billions of years in the past. Each particle of light is a voyager crossing cosmic expanses to arrive at our instruments. A simple look at a deep space photograph is truly a vision into prehistory, an opening through which the past continues to burn softly alive within the present. It is peculiar to realize that light can outlast the origins it departed from. Some of those galaxies may have ceased to exist. Their suns dispersed, their forms dissolved by collisions or the passage of time, yet their light persists, carrying the imprint of what once flourished. Telescopes do not merely show the distant universe, they demonstrate its endurance. Each observation becomes an exercise in time travel, a method of reaching toward the universe, not as it exists now, but as it once imagined itself into being. This temporal displacement creates a strange intimacy with the past. When you look at a galaxy 10 billion light-years away, you are seeing it as it was 10 billion years ago. The stars visible in that galaxy have likely all died by now. New generations of stars have been born, lived their lives, and died in turn. The galaxy itself has probably merged with neighbors, transformed its shape, evolved into something entirely different. Yet here, in our telescopes, it remains frozen in time, a permanent record of what it once was. In a sense, distant galaxies are immortal. Even after they change beyond recognition, even after they cease to exist entirely, their ancient light continues spreading through space, carrying the memory of their youth to distant observers who may see them billions of years after they are gone. We are those observers, witnesses to ghosts that continue to shine long after the sources have faded. There is something poetic in this arrangement. The universe preserves its own history in the light that travels through it. Every moment of cosmic history is encoded somewhere in the stream of photons filling space. The early universe, the formation of the first stars, the assembly of the first galaxies, all of these events continue to exist as traveling light, visible to any observer positioned at the right distance. If you could travel far enough, fast enough, you could theoretically catch up to light emitted from Earth billions of years ago, watching ancient history play out as if it were happening now. Of course, the distances involved make this impossible, but the principle remains. The past is not truly gone. It lives on in the light, spreading through space, accessible to anyone with the instruments to capture it. When astronomers discuss the observable universe, they are not referring to the totality of existence, only the portion that light has managed to reach us from. Beyond that invisible edge, the universe extends, perhaps without limit. The barrier is not made of substance. It is constructed from time, determined by the age of existence itself. We find ourselves encircled by a cosmic boundary, roughly 46 billion light-years distant in all directions. A sphere composed not of matter but of duration, expanding as the universe ages. Everything past that boundary stays invisible, its light still journeying through emptiness. One day, countless ages from now, even neighboring galaxies will drift beyond perception as cosmic expansion pulls them away faster than light itself can chase. What we call the observable universe is merely our local bubble of duration, a fleeting window carved from physics and circumstance. And inside that fragile sphere, we seek understanding, counting galaxies we were never intended to witness. The size of the observable universe, 46 billion light-years, might seem paradoxical. If the universe is only about 14 billion years old, how can we see objects 46 billion light-years away? Should not the observable radius be only 14 billion light-years? The answer lies in expansion. When light was emitted from a distant galaxy billions of years ago, that galaxy was much closer to us than it appears now. As the light traveled toward us, space itself expanded, stretching the distance between us and that galaxy. By the time the light arrived, the galaxy had been carried away by expansion to a much greater distance. So, while the light has been traveling for perhaps 13 billion years, the source of that light is now more than 40 billion light-years away. This expansion of space creates a peculiar geometry where the observable universe is significantly larger than one might naively expect from its age alone. The observable universe is sometimes called our cosmic horizon, and like any horizon, it represents the limit of what we can see, not the limit of what exists. Just as a person standing on a ship in the middle of the ocean can see only to the horizon, beyond which more ocean extends unseen, we can see only to our cosmic horizon, beyond which more universe likely extends indefinitely. But there is a crucial difference. The ocean horizon expands as you move forward, always keeping the same distance away. The cosmic horizon, however, changes with time, not with our position. As the universe grows older, light from more distant regions has time to reach us, and our observable universe slowly expands. But simultaneously, cosmic expansion is pushing distant galaxies away from us, and those near the edge of observability are being carried away faster and faster. Eventually, they will cross a threshold where the expansion of space between us and them exceeds the speed of light, and they will vanish from view forever, slipping beyond our cosmic horizon into a realm we can never observe. This creates a troubling future scenario. As dark energy, the mysterious force driving accelerating cosmic expansion, continues to push galaxies apart, the observable universe will gradually shrink. Distant galaxies will redshift beyond detectability. Galaxy clusters will separate. Eventually, billions of years from now, an observer in our galaxy will see a universe almost empty of galaxies. Our local group, the Milky Way and Andromeda, and a few dozen smaller galaxies bound together by gravity, will be all that remains visible. Everything else will have been carried beyond the horizon by expansion. Future civilizations, if they exist, might look out and conclude they live in a nearly empty universe, unaware of the trillions of galaxies that exist beyond their cosmic horizon. They would face the inverse of our current challenge. We struggle to see the most distant galaxies. They would struggle to see any galaxies at all. At first, the task appears uncomplicated. Count what becomes visible and multiply accordingly. But the universe refuses to make it simple. Every telescope, regardless of its strength, captures only a fragment of the celestial dome. What we gather are statistical samples, not a complete census. Some galaxies hide behind clouds of dust. Others exist beyond our threshold of detection. Even the faintest radiation may vanish beneath cosmic background interference. To measure everything, astronomers must depend on models, mathematics, and a touch of imagination. Each observation serves as evidence, not a definitive answer. From a narrow patch of deep space, scientists estimate how many galaxies ought to populate the entire sphere of heavens. But the universe does not distribute itself evenly. Matter accumulates and disperses, voids spread across hundreds of millions of light years. A single deep field might capture one cosmic region, not the average of all regions. Counting galaxies, therefore, is not an exercise in simple calculation. It is an act of inference, a way of outlining infinity with constrained illumination. The mathematics involved are complex but elegant. Astronomers observe a small patch of sky, perhaps 1/10,000,000th of the entire celestial sphere. Within that tiny region, they count every galaxy they can detect, from the brightest to the faintest. Then comes the extrapolation. If this small region contains, say, 5,000 galaxies, and the entire sky is 10 million times larger, then perhaps the universe contains 50 billion galaxies. But this simple multiplication hides numerous complications. The universe is not uniform. Some regions are denser than others. The small patch observed might sit within a cluster of galaxies, making it unusually crowded. Or it might lie within a void, making it unusually sparse. To account for this, astronomers observe multiple patches in different directions, building a statistical average. They also must account for galaxies too faint to see, those that exist but remain below the detection threshold of current instruments. Mathematical models help estimate how many invisible galaxies hide in the darkness for every visible one detected. The final number is not a precise count, but a probabilistic estimate, a range within which the true number likely falls. These estimates have evolved dramatically over time. Early estimates from ground-based telescopes in the mid-20th century suggested perhaps 10 million galaxies in the observable universe. Hubble's deep field observations in the 1990s raised that estimate to around 100 billion. More recent deep field observations with Hubble, combined with infrared surveys and mathematical modeling, pushed the estimate to around 200 billion. Now, with Webb's unprecedented sensitivity revealing previously invisible galaxies, some astronomers suggest the number might exceed 2 trillion. Each improvement in our instruments reveals more galaxies, pushing the total ever higher. And yet we remain convinced that even this enormous number represents only what we can currently detect. There may be populations of galaxies, perhaps very small ones, or very diffuse ones, that remain beyond our current ability to observe. The farther we peer into the universe, the more misleading it becomes. Light does not merely travel, it elongates, curves, and weakens with distance. As space swells, the wavelength of that light grows longer, transforming visible hues into red-shifted murmurs from the ancient past. A galaxy appearing as a tiny crimson smudge might in reality be enormous and blazing, but its light has aged across billions of years during its journey here. We observe not the galaxy as it stands, but as it once stood, its true shape hidden beneath layers of cosmic transformation. This redshift becomes both barrier and compass. It tells astronomers how far away a galaxy exists, and therefore how far back in time they are gazing. The deeper the red, the more ancient the light. But it also makes detection extraordinarily difficult. Light stretched into the infrared becomes invisible to traditional telescopes, slipping past optical sensors like a ghost. For decades, the earliest galaxies remained hidden not because they did not exist, but because we lacked the ability to perceive them. To count galaxies across cosmic history, we need instruments capable of capturing this ancient, transformed light. We need eyes that can see through billions of years of expansion, that can register wavelengths so red they border on invisibility. For most of human astronomy, such eyes did not exist. We could map the nearby cosmos, but could only speculate about the ancient universe. The true census remained impossible, locked behind a veil of stretched starlight, waiting for technology to catch up with our questions. That waiting, it turns out, was necessary, because what we would eventually discover would overturn nearly everything we thought we knew. Redshift is measured as a number called Z. A redshift of 0 means no shift at all, indicating an object at rest relative to us. A redshift of 1 means the light's wavelength has doubled during its journey. A redshift of 2 means it has tripled. The most distant galaxies observed by Webb have redshifts exceeding 13, meaning their light has been stretched to more than 14 times its original wavelength. At such extreme redshifts, ultraviolet light emitted by hot young stars gets shifted all the way into the infrared, completely invisible to optical telescopes like Hubble, but perfectly detectable by Webb's infrared sensors. This is why Webb was designed specifically to observe in the infrared. Not because infrared light is inherently more interesting, but because it is the only way to see the most distant, most ancient parts of the universe. The farther back in time we wish to look, the more we must shift our gaze into redder wavelengths. The relationship between redshift and distance is encoded in Hubble's law, though the details are more complex than Hubble originally understood. In the nearby universe, redshift is proportional to distance. Double the distance, double the redshift. But for very distant objects, the relationship becomes non-linear, affected by the expansion history of the universe, the density of matter and dark energy, and the geometry of space-time itself. Cosmologists use complex models incorporating these factors to convert observed redshifts into distances and look-back times. A galaxy at redshift 1 is seen as it was roughly 8 billion years ago, when the universe was about 6 billion years old. A galaxy at redshift 6 is seen as it was 12 billion years ago, when the universe was less than 1 billion years old. And galaxies at redshift 13 or higher show us the universe in its infancy, just a few 100 million years after the Big Bang, when the first stars and galaxies were forming. For centuries, philosophers and scientists debated the size of the cosmos. Some believed it was small and enclosed, a celestial sphere rotating above the Earth. Others suspected it might extend without limit, but belief was all they had. Actual evidence remained elusive, hidden beyond the reach of their instruments and methods. The tools were too crude, the sky too vast. And so, the question of scale lingered unresolved, a puzzle with pieces scattered across time. Then came the early 20th century, and with it, a transformation in our understanding. New telescopes, larger and sharper than ever before, began to resolve the smudges and nebulae that had confused earlier generations. Astronomers could now measure distances, not just positions. They could trace the motion of stars and clouds across years of observation. And most critically, they could analyze light itself, breaking it into spectra that revealed composition, temperature, and movement. Spectroscopy became the key that unlocked the cosmos. By passing starlight through a prism or diffraction grating, astronomers could spread it into a rainbow of colors, each color corresponding to a specific wavelength. Within this rainbow appeared dark lines, absorption features where specific wavelengths had been absorbed by elements in the star's atmosphere. Each element produces a unique pattern of lines, a spectral fingerprint that identifies its presence. Hydrogen produces one pattern, helium another. Iron, calcium, oxygen, each has its own signature. By studying these patterns, astronomers could determine what stars and nebulae were made of without ever visiting them. And more importantly, they could measure how fast objects were moving. If a star or galaxy was moving away from us, its spectral lines would shift toward the red end of the spectrum. If moving toward us, the lines would shift toward blue. This Doppler shift, similar to the way a siren's pitch changes as an ambulance passes, became a tool for measuring cosmic velocities and, ultimately, cosmic distances. The power of spectroscopy cannot be overstated. Before its development, astronomers could only measure where celestial objects were and how bright they appeared. With spectroscopy, they could suddenly determine what objects were made of, how hot they were, how fast they were moving, whether they were approaching or receding, and even the physical conditions in their atmospheres. The science of astrophysics, as opposed to mere positional astronomy, began with spectroscopy. It transformed astronomy from a descriptive science into a physical one, allowing astronomers to apply the laws of physics to distant objects and understand their nature. The discovery that distant galaxies showed redshifts, and that these redshifts increased with distance, led directly to the understanding that the universe is expanding, perhaps the most profound discovery in the history of cosmology. One astronomer in particular would use these tools to reshape our understanding of existence. Edwin Hubble, working from Mount Wilson Observatory in California, turned his attention to a faint nebula known as Andromeda. Inside it, he identified something remarkable, a type of star called a Cepheid variable, whose brightness pulsed in regular cycles. Astronomers had already discovered that these pulsations were linked to the star's true luminosity. By comparing how bright the star appeared with how bright it actually was, they could calculate its distance. When Hubble performed this calculation for Andromeda, the result was staggering. The nebula was not part of the Milky Way. It was over 2 million light-years away, far beyond the boundaries of our galaxy. It was, in fact, a galaxy itself. Andromeda was not a cloud of gas or a cluster of nearby stars. It was an entire island of hundreds of billions of suns, a sister galaxy floating in the void. Imagine the shock of this discovery. For all of human history, the Milky Way had been the universe. Every star, every nebula, every celestial object had been assumed to belong to our galactic home. Now, in a single observation, that assumption was shattered. Andromeda was not just far away. It was incomprehensibly far, at a distance that dwarfed anything previously measured. And if Andromeda was a separate galaxy, what about the other spiral nebulae scattered across the sky? The implications cascaded through astronomy like falling dominoes. Each of those faint smudges might be another galaxy, another island universe, each containing billions of stars. The cosmos was not a single structure, but a vast archipelago of galaxies, separated by distances so great that their light took millions of years to cross the void between them. Hubble's discovery was made possible by the work of Henrietta Leavitt, an astronomer at Harvard College Observatory who had studied Cepheid variables in the Small Magellanic Cloud, a satellite galaxy of the Milky Way. Leavitt discovered that there was a precise relationship between a Cepheid's period, how long it took to go through one cycle of brightening and dimming, and its absolute luminosity, how much light it actually emitted. This period luminosity relationship meant that by measuring a Cepheid's period, which was easy to do, astronomers could determine its absolute luminosity. And by comparing that to how bright it appeared, they could calculate its distance. This made Cepheids standard candles, objects whose true brightness is known, allowing distances to be measured accurately. Hubble found Cepheids in Andromeda and used Leavitt's relationship to calculate its distance, proving once and for all that Andromeda was far beyond the Milky Way. The revelation did not stop there. Hubble went on to measure other nebulae, finding them at distances that dwarfed anything previously imagined. Each one was a separate galaxy. The Milky Way, once thought to contain everything, was revealed to be just one galaxy among countless others. The universe was not a single city. It was a metropolis of cities, each one vast, each one home to billions of stars. The philosophical implications were immense. Humanity had once believed Earth was the center of the cosmos. Then we learned the sun was the center. Then we realized the sun was just one star among many. Now, we discovered that even our galaxy was not unique. We lived in one neighborhood of an unimaginably vast cosmic landscape. The scale of existence had exploded outward, and with it, our sense of place. Hubble's discoveries also opened a new question. If galaxies were scattered throughout space, how many were there? And could we ever hope to count them all? These questions would drive astronomy for the next century, pushing the limits of technology and imagination. The journey to answer them would lead us deeper into space, farther back in time, and closer to the fundamental truths of the cosmos itself. Hubble made another discovery that would prove even more revolutionary. As he measured the distances to galaxies and their velocities using redshift, he noticed a pattern. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship, later called Hubble's law, suggested something extraordinary. The universe was not static, it was expanding. Every galaxy was moving away from every other galaxy, not because they were flying through space, but because space itself was growing, carrying galaxies along with it like raisins in rising bread dough. This discovery would lead to the Big Bang theory, the understanding that the universe had a beginning, a moment roughly 14 billion years ago when all matter and energy were concentrated in an infinitely small point before exploding outward in the greatest expansion event in history. The implications were staggering. If the universe was expanding, then looking backward in time meant looking toward a denser, hotter, younger cosmos. The farther back we looked, the closer we approached the moment of creation itself. The expanding universe was not an easy concept to accept. It implied that the universe had not always existed in its current state, that there was a beginning to time itself. This ran counter to centuries of philosophical thinking that assumed the universe was eternal and unchanging. Einstein himself initially resisted the idea, adding a cosmological constant to his equations to keep the universe static. When Hubble's observations proved expansion was real, Einstein reportedly called this his greatest blunder. Yet the expanding universe, once accepted, provided a framework for understanding cosmic history. If we could measure the current rate of expansion, we could work backwards and determine when the expansion began. This became one of the primary goals of observational cosmology, measuring the Hubble constant, the rate of cosmic expansion, with sufficient precision to determine the age of the universe accurately. By the mid-20th century, astronomers had mapped thousands of galaxies, but the total number remained a mystery. Telescopes could only see so far, beyond a certain distance. Galaxies faded into the background glow of the universe, indistinguishable from noise. To make progress, scientists needed a new approach, a way to peer deeper than ever before. The solution came from space. In 1990, NASA launched the Hubble Space Telescope, an instrument unlike any that had come before. Positioned above Earth's atmosphere, it could observe without the blurring effects of air and light pollution. Its mirrors were polished to exquisite precision. Its cameras could capture wavelengths invisible to the human eye. And most importantly, it could stare at a single patch of sky for hours, even days, accumulating faint light that ground-based telescopes would miss. Earth's atmosphere, while essential for life, is a nightmare for astronomers. Air molecules scatter light, causing stars to twinkle and images to blur. Turbulence creates pockets of varying density that bend light unpredictably, smearing fine details. Water vapor absorbs infrared and ultraviolet light, making entire regions of the spectrum invisible from the ground. Even on the clearest night, at the best mountaintop observatory, the atmosphere limits what we can see. Placing a telescope in space eliminates all of these problems. Above the atmosphere, stars shine steady and sharp. Images remain perfectly focused. And the entire electromagnetic spectrum becomes accessible, from ultraviolet to infrared, without atmospheric interference blocking our view. The Hubble Space Telescope was humanity's first great eye in space, and it would transform our understanding of the universe more profoundly than any instrument since Galileo's original telescope 4 centuries earlier. The decision to build a space telescope was not without controversy. The costs were enormous, the technical challenges daunting. Launching a telescope weighing over 11 tons into orbit required extraordinary engineering. The mirror had to be ground to unprecedented precision, accurate to within a few wavelengths of light across its entire 2.4-meter diameter. The instruments had to survive the violence of launch, the harsh environment of space, and operate remotely for years without maintenance, and there was risk. If something went wrong during launch or deployment, the mission could be lost entirely, along with billions of dollars and decades of work. But the scientific potential was too great to ignore. A telescope above the atmosphere could observe fainter objects, see sharper details, and access wavelengths impossible from the ground. It could revolutionize astronomy, and it did. In 1995, astronomers decided to use Hubble for an audacious experiment. They aimed it at a seemingly empty region of sky, a patch no larger than a grain of sand held at arm's length. This area, near the Big Dipper, appeared utterly dark to the naked eye. No stars, no nebulae, nothing. For 10 consecutive days, Hubble held its gaze there, collecting every photon it could. When the image was finally assembled, astronomers were stunned. The darkness was teeming with light. The image revealed not emptiness, but thousands of galaxies, each one a faint smudge of ancient starlight. Some were nearby, large and well-defined. Others were so distant their light had traveled for billions of years. These were galaxies from the early universe, their forms stretched and reddened by cosmic expansion. The photograph became known as the Hubble Deep Field, and it changed everything. If such a tiny sliver of sky contained thousands of galaxies, then the entire heavens must hold billions, perhaps even trillions. The universe was far more crowded than anyone had imagined. The choice of target was deliberate and risky. Pointing Hubble at an empty patch of sky meant sacrificing 10 days of telescope time that could have been spent observing known objects, cataloguing stars, or studying nearby galaxies. Many astronomers questioned the decision. What if the empty patch really was empty? What if the long exposure revealed nothing but a few faint stars? The telescope time would be wasted, and the project would be remembered as a costly failure. But the director of the Space Telescope Science Institute, Robert Williams, believed the risk was worth taking. If the empty sky contained hidden galaxies, the discovery would be revolutionary. And so, the observation went forward, with Hubble staring into apparent nothingness for over 150 hours, accumulating photons one by one. The gamble paid off beyond anyone's wildest expectations. When the Hubble Deep Field image was released to the public, it became an icon of modern astronomy. The picture showed approximately 3,000 galaxies in a region of sky smaller than a pencil eraser held at arm's length. If that tiny patch contained 3,000 galaxies, simple arithmetic suggested the entire sky must contain billions. The image sparked public imagination, appearing in museums, planetariums, and science documentaries around the world. It became a symbol of the vastness of the universe and the power of human curiosity. For astronomers, it was a treasure trove of data. Each galaxy in the image could be studied individually, its redshift measured, its distance calculated, its properties analyzed. The deep field revealed galaxies at various stages of evolution, from nearby mature spirals to distant irregular blobs representing early galactic assembly. It became one of the most studied images in astronomical history. The discovery was not just quantitative, it was philosophical. Each of those faint points was a galaxy, home to billions of stars, possibly trillions of planets, and who knows how many stories. The image was a reminder of scale, of insignificance, and paradoxically, of connection. We were looking at the universe as it had been long before our solar system existed, and yet we were part of that same unfolding story. Hubble would go on to capture even deeper images, pushing farther into the past. The ultra-deep field, taken over the course of nearly 12 days, revealed galaxies from the universe's infancy, just a few 100 million years after the Big Bang. These were some of the first structures to emerge from the cosmic dawn, primitive and irregular, but unmistakably the ancestors of modern galaxies. The deeper we looked, the more we found. And the more we found, the clearer it became that our understanding of the universe was still incomplete. Each image raised new questions. How did these early galaxies form? What made them grow into the grand spirals and ellipticals we see today? and what lies even farther back in the epochs we have yet to observe? The answers would require something even more powerful than Hubble, something capable of seeing not just farther, but clearer, something that could capture the faintest whispers of light from the edge of time itself. That instrument was already being imagined, designed, and built. It would carry the hopes of an entire generation of astronomers, and it would reveal a universe stranger and more beautiful than anyone expected. Hubble's deep-field images also revealed something else: the sheer diversity of galaxy types. Some galaxies were perfect spirals, with elegant arms winding outward from a bright central bulge. Others were featureless ellipticals, looking like glowing rugby balls or spheres with no discernible structure. Still others were irregular, chaotic jumbles of stars with no clear shape at all. And many were interacting, colliding with neighbors in slow-motion cosmic ballets that would last millions of years. This diversity hinted at complex evolutionary pathways. Galaxies were not born in their final forms. They grew, changed, merged, and transformed over billions of years. By observing galaxies at different distances, astronomers were essentially sampling different eras in cosmic history, seeing galaxies at various stages of development. The nearest galaxies showed what galaxies look like today, mature and well-organized. The most distant showed galaxies in their youth, smaller, more chaotic, still in the process of assembly. Together, these observations began to paint a picture of galactic evolution, a story of how simple structures grew into the complex, majestic galaxies we see in the modern universe. Galaxy morphology, the study of galaxy shapes and structures, became a field unto itself. Edwin Hubble had created a classification scheme, the Hubble sequence or tuning fork diagram, that organized galaxies into types based on their appearance. Elliptical galaxies, labeled E, followed by a number indicating their degree of flattening, were smooth and featureless. Spiral galaxies, labeled S, had distinct arms and central bulges. Barred spirals, labeled SB, had a bar-shaped structure through their centers with arms emerging from the ends of the bar. Irregular galaxies had no clear structure. This classification was observational, based purely on appearance, but astronomers soon realized it also reflected evolutionary history. Ellipticals tended to be older, made of old red stars with little ongoing star formation. Spirals were younger, with active star formation in their arms. Mergers between spirals typically produced ellipticals, destroying the delicate structures and creating featureless blobs. The Hubble sequence was not a timeline, with galaxies evolving from one type to another, but rather a snapshot of different outcomes from different formation histories. In the early 2000s, engineers and scientists around the world began working on a successor to Hubble. This new telescope would be larger, more sensitive, and optimized for a specific task. Observing the universe in the infrared, the stretched, reddened light from the most distant galaxies, it would be called the James Webb Space Telescope, and it would become the most complex scientific instrument ever launched into space. Unlike Hubble, which orbits Earth, Webb would be positioned much farther away, at a gravitational balance point nearly 1 million miles from our planet. There, shielded from the sun's heat by a tennis court-sized sunshield, it could cool to temperatures just above absolute zero. This extreme cold was essential. Infrared detectors must be kept frigid to avoid interference from their own heat. Webb's mirror was designed to be enormous, over 6 meters across, giving it the light-gathering power needed to capture the faintest signals. But it was too large to fit inside any rocket, so engineers devised a way to fold it, origami style, for launch. Once in space, it would unfold itself in a delicate, choreographed sequence. If any step failed, the mission would be lost. The stakes were staggering. The project took over 2 decades to complete. Costs soared into the billions. Skeptics questioned whether it would ever launch, but the vision persisted. This telescope would not just look at distant galaxies, it would look at the cosmic dawn, the era when the first stars and galaxies ignited. It would peer into star-forming regions, watching planets being born. It would analyze the atmospheres of distant worlds, searching for signs of habitability. The engineering challenges were immense. Webb's sunshield had to unfold in space to the size of a tennis court, a process involving hundreds of mechanisms that all had to work perfectly in the harsh environment of space. The mirror segments, 18 hexagonal pieces of gold-coated beryllium, had to align with each other to nanometer precision, essentially forming a perfect mirror despite being assembled from separate pieces. The spacecraft had to travel to a point called Lagrange 2, 1,000,000 miles from Earth, where it would balance between the gravitational pulls of Earth and Sunday. And once there, it had to operate flawlessly because unlike Hubble, which astronauts could visit for repairs, Webb would be far too distant for any repair mission. If something went wrong, the mission would end. The pressure on the team was intense. Thousands of people worked for decades to make this telescope a reality, knowing that the entire project depended on everything functioning perfectly the first time. The deployment sequence alone was a marvel of engineering and a source of enormous anxiety. Over 300 single-point failures had been identified, any one of which could doom the mission. The sunshield consisted of 5 layers of Kapton film, each as thin as a human hair, that had to unfold in sequence. The mirror segments had to be released from their folded launch configuration and moved into position using tiny motors. The secondary mirror, suspended on a tripod in front of the primary mirror, had to extend and lock into place. Every mechanism had been tested exhaustively on the ground, but space is an unforgiving environment. Temperature extremes, vacuum, radiation, all could affect the delicate systems. The deployment would take 2 weeks, and during that time, the entire astronomical community held its breath, waiting to see if this 20-year, $10 billion project would succeed or fail. On Christmas Day, 2021, the James Webb Space Telescope finally launched. The world held its breath as it climbed away from Earth, unfolded its sunshield, deployed its mirror segments, and began its journey to its distant orbital home. 6 months later, after a tense commissioning phase, the first images arrived, and they were breathtaking. Webb's first deep-field image showed a region of space in sharper detail than ever before. Galaxies that appeared as fuzzy blobs in Hubble's images now revealed intricate structures, spiral arms, star clusters, collisions. And behind them, thousands more galaxies stretched into the distance, layer upon layer of cosmic history. Astronomers immediately began analyzing the data, and what they found was astonishing. In ways both exciting and unsettling, Webb revealed that the early universe was far more complex, more organized, and more mature than theory had predicted. Galaxies that should have been small and chaotic were instead large and structured. Stars were forming at rates that models had not anticipated. The timeline of cosmic evolution, painstakingly constructed over decades, was suddenly in question. Webb had not simply confirmed what we thought we knew. It had challenged it, and in doing so, it had opened the door to a deeper understanding of how the universe truly came to be. The discoveries continue. Each week brings new images, new spectra, new mysteries. The telescope is still in its early years of operation, and already it has transformed our view of the cosmos. What lies ahead is uncertain, but one thing is clear. The James Webb Space Telescope has given humanity a gift: the ability to see not just the universe as it is, but the universe as it was, in its earliest, most formative moments. And in those moments, we find the origins of everything we know. Webb's instruments are not just cameras. They are sophisticated spectrographs capable of breaking light into thousands of individual wavelengths, revealing the detailed chemical composition and physical conditions of distant objects. This spectroscopic capability allows Webb to do more than just take pictures. It can analyze the atmospheres of exoplanets, searching for water vapor, carbon dioxide, methane, and other molecules that might indicate habitability or even life. It can measure the exact redshifts of distant galaxies with extreme precision, determining their distances and velocities. It can identify the elements present in early galaxies, revealing how quickly heavy elements were produced by the first generations of stars. In many ways, spectroscopy is even more valuable than imaging. A picture shows what an object looks like. A spectrum reveals what it is made of, how it is moving, and what physical processes are occurring within it. Webb carries 4 main instruments. The Near-Infrared Camera, or NIRC cam, is the primary imager, capturing stunning photographs of distant galaxies. The Near-Infrared Spectrograph, NIRSpec, can observe up to 100 objects simultaneously, gathering detailed spectra efficiently. The Mid-Infrared Instrument, MIRI, observes at longer wavelengths, seeing cooler objects and dust clouds. And the Near-Infrared Imager and Slitless Spectrograph, NIRIS, specializes in exoplanet studies and wide-field imaging. Together, these instruments make Webb the most versatile infrared observatory ever built. Each instrument took years to develop, requiring new detector technologies, new optical designs, and new calibration techniques. The result is an observatory capable of observing the universe across a wide range of infrared wavelengths with unprecedented sensitivity and resolution. Among the most profound revelations from Webb is what it shows us about the cosmic dawn, the era when the first stars and galaxies emerged from darkness. For most of cosmic history, the universe was a cold, dark sea of hydrogen and helium. No stars existed, no light pierced the void. This period is called the Dark Ages, a time lasting hundreds of millions of years. But eventually, gravity began to pull matter together. Dense pockets of gas collapsed, heating until nuclear fusion ignited. The first stars were born. These earliest suns were nothing like the stars we see today. They were massive, hundreds of times the mass of our sun, burning fiercely and dying quickly in explosive supernovae. Their deaths seeded space with heavier elements, carbon, oxygen, iron, the building blocks of planets and life. Around these first stars, small galaxies began to form, collections of millions of stars bound together by gravity. These were the seeds of everything that would come after. The first stars are sometimes called population. 3 stars, a classification that seems backwards until you understand the history. Astronomers initially classified stars into 2 populations. Population 1 stars, like our Sun, which are metal-rich and found in the disks of galaxies. And population 2 stars, which are metal-poor and found in the halos of galaxies and in globular clusters. The term metal in astronomy refers to any element heavier than helium, so even carbon and oxygen are considered metals. Population 2 stars have very few metals, suggesting they formed earlier when the universe had not yet produced much of these heavier elements. When astronomers realized there must have been an even earlier generation of stars completely devoid of metals, they called them population 3. These stars have never been observed directly. They existed so long ago and were so short-lived that they are all long since dead. But Webb is now searching for their signatures, and possibly even direct observations of the last remaining population 3 stars, if any still exist in the most distant reaches of space. The search for population 3 stars is one of the holy grails of modern astronomy. If Webb could detect even one such star, it would revolutionize our understanding of the early universe. These stars would have properties unlike anything we see today. With no metals to help them radiate away heat, they would have been extraordinarily hot and bright, perhaps reaching temperatures over 100,000 degrees at their surfaces. They would have been incredibly short-lived, perhaps only a few million years from birth to death, compared to the billions of years typical stars like our Sun will live. And their deaths would have been spectacular, exploding as supernovae and scattering the first heavy elements into the surrounding space. These elements would then be incorporated into the next generation of stars, beginning the process of cosmic chemical enrichment that eventually led to planets and life. Before Webb, astronomers had only glimpsed hints of these primordial galaxies. Hubble could see back to within a few 100 million years of the Big Bang, but the most distant galaxies appeared as faint, blurry smudges. Their details were lost. Webb, with its infrared vision, has changed that. It can see galaxies from just a few 100 million years after the universe began, capturing them in stunning clarity, and what it reveals is surprising. These early galaxies are not the small, chaotic clumps that models predicted. Many are surprisingly large, surprisingly bright, and surprisingly organized. Some already show signs of spiral structure, a feature that was thought to take billions of years to develop. Others are forming stars at astonishing rates, far faster than theory suggested was possible so early. This has created what some astronomers call the impossibly early galaxy problem. According to our understanding of how galaxies grow, these structures should not exist yet. There should not have been enough time for so much matter to collect, for so many stars to form, for such order to emerge. Yet there they are, shining in Webb's images, defying expectations. The problem is not that the observations are wrong. Webb's data is incredibly precise. The problem is that our models may be incomplete. Perhaps dark matter behaves differently than we thought. Perhaps star formation in the early universe was more efficient. Perhaps galaxies merged and grew faster than we imagined. These questions are now at the forefront of cosmology, and Webb is providing the clues needed to answer them. Some astronomers have proposed that these massive early galaxies formed through a process called monolithic collapse, where large clouds of gas collapsed directly into galaxies without first forming smaller structures that later merged. Others suggest that the initial conditions of the universe, the distribution of matter in the moments after the Big Bang, may have been slightly different than our models assume, leading to faster structure formation. Still others wonder if our understanding of star formation itself needs revision. Perhaps young galaxies converted gas into stars far more efficiently than modern galaxies do. Or perhaps the initial mass function, the distribution of stellar masses when stars form, was different in the early universe, favoring more massive stars that would shine more brightly and produce more light from the same amount of matter. These are not small questions. They touch on fundamental aspects of cosmology, from the nature of dark matter to the physics of star formation to the structure of space-time itself. The initial mass function is a particularly interesting problem. In the modern universe, when a cloud of gas collapses to form stars, it produces mostly small stars, with progressively fewer stars at higher masses. For every massive star like Sirius or Betelgeuse, there are thousands of small stars like red dwarfs. This distribution seems to be roughly universal in nearby star-forming regions, but was it the same in the early universe? If the first generation of stars tended to be more massive on average, they would have been much brighter, making early galaxies appear more luminous than expected for their mass. They also would have died quickly in supernovae, rapidly enriching the interstellar medium with heavy elements. Some theoretical models suggest that the absence of metals in the first gas clouds would have made it easier for large stars to form and harder for small ones. If true, This would help explain why early galaxies appear so bright and so chemically enriched. One particularly striking discovery involves massive galaxies appearing within the first billion years of cosmic history. These galaxies contain billions of stars, masses that rival some of the largest galaxies in the modern universe. How did they assemble so quickly? The leading theory involves rapid mergers, small galaxies colliding and combining at an accelerated pace, driven by the denser conditions of the early universe. Another discovery involves supermassive black holes. At the centers of many large galaxies, including our own Milky Way, sit black holes with masses millions or even billions of times that of the Sun. Webb has found galaxies from the cosmic dawn that already harbor these giants. How did black holes grow so massive so quickly? This question challenges our understanding of black hole formation and growth. Some astronomers suggest that black holes may have formed directly from collapsing clouds of gas, bypassing the usual process of forming from dying stars. Others propose that early black holes fed on surrounding matter at rates far exceeding what we see today. Webb's ability to analyze the light from these distant galaxies is also revealing their chemical composition. By breaking light into its component wavelengths, astronomers can identify which elements are present. Early galaxies show surprising amounts of heavier elements, suggesting that the first generations of stars lived and died quickly, enriching their environments. This rapid chemical evolution helps explain how later generations of stars and planets, including our own solar system, could form. The cosmic chemistry is a story in itself. The Big Bang produced only the lightest elements, hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon in your body, every breath of oxygen, every grain of silicon in the Earth's crust, was forged inside stars. When massive stars die in supernova explosions, they scatter these heavier elements into space, enriching the surrounding gas. The next generation of stars that forms from this gas will have more metals, and their planets will be rocky rather than purely gaseous. This process of cosmic enrichment took billions of years, gradually building up the periodic table element by element. The earliest galaxies had almost no metals. But with each generation of stars, with each supernova, the metal content increased. By analyzing the spectra of distant galaxies, Webb can measure how quickly this enrichment happened, providing a timeline for when the universe became capable of forming Earth-like planets and, potentially, life. Different elements are produced by different processes. Carbon, oxygen, and nitrogen are made in the cores of massive stars during their normal lifetimes through successive fusion reactions. Silicon, sulfur, and iron are produced in the final moments before a supernova, as the core of the star collapses and temperatures reach billions of degrees. Elements heavier than iron, like gold and platinum and uranium, cannot be produced by normal fusion because it requires more energy than it releases. Instead, these elements are made in the most violent events in the universe, neutron star mergers, and perhaps some types of supernovae, where conditions are so extreme that rapid neutron capture can occur. Each element has its own origin story, and by measuring the abundances of different elements in early galaxies, astronomers can reconstruct the history of stellar populations, determining what types of stars lived and died and in what proportions. The cosmic dawn is not just a phase in history, it is the foundation. Everything we see in the universe today, every galaxy, every star, every planet, traces its origins back to those first few 100 million years. Webb is allowing us to witness that foundation being laid, to see the universe in its infancy, raw and unformed, but already brimming with potential. There is something deeply moving about these images. To look at a galaxy from 13 billion years ago is to look at a time before our galaxy existed, before our Sun, before Earth. It is to see the universe as it once was, young and turbulent, beginning its long journey toward the present. And it is to realize that we are connected to that beginning, that the atoms in our bodies were forged in those ancient stars, that our existence is tied to the cosmic dawn in ways both profound and humbling. Think about the journey those atoms have taken. Hydrogen formed in the Big Bang, floating through space for hundreds of millions of years, drawn by gravity into the first stars, where it was fused into heavier elements, scattered by supernova explosions across vast distances, incorporated into the next generation of stars, and the next, each cycle adding more complex elements, eventually finding their way into a cloud of gas and dust in one arm of a young spiral galaxy, collapsing under gravity to form a new star, our Sun, and around it, planets. One of those planets, the third from the Sun, became home to liquid water, complex chemistry, and eventually life. Life that evolved over billions of years into creatures capable of looking back across cosmic time and contemplating their own origins. Every atom in your body has been on a journey billions of years long, cycling through multiple stars, traveling across the galaxy, finally arriving here, temporarily assembled into the form of a thinking, wandering being, before eventually returning to the cosmos when this brief chapter ends. This atomic recycling is not abstract, it is literal. The calcium in your bones was produced in a supernova explosion billions of years ago. The iron in your blood was forged in the core of a dying star. The oxygen you breathe was created by massive stars and scattered into space when they exploded. Even the water molecules in your cells. The hydrogen is primordial from the Big Bang, but the oxygen is stellar, created and dispersed by stars. You are not separate from the universe, you are made of it. Your body is assembled from the ashes of long dead stars, and when you die, those atoms will return to the Earth, and eventually, over geological timescales, some may be recycled into space, perhaps to be incorporated into future stars and planets. The matter that makes you is temporary. The atoms themselves are nearly eternal, cycling through the cosmos in an endless dance of creation and destruction. The more we learn, the more questions arise. What triggered the first stars to form? How did galaxies organize themselves so quickly? What role did dark matter play? Why do some galaxies grow massive while others stay small? Webb cannot answer everything, but it is giving us the tools to ask better questions, to refine our theories, and to inch closer to understanding the origins of the cosmos. And perhaps most importantly, it is showing us that the universe is not a static place. It is dynamic, evolving, full of surprises. The story of creation did not end with the Big Bang. It continues, written in the light of distant galaxies, waiting for us to read. Each discovery with Webb seems to raise two new questions for every answer it provides. This is the nature of science at the frontier. We push into the unknown, expecting to find confirmation of our theories, and instead we find something unexpected that challenges our assumptions. This can be frustrating, but it is also exhilarating. It means we are truly exploring, truly discovering, not just confirming what we already believe, but learning something genuinely new about the universe. The impossibly early galaxies are a perfect example. They do not fit neatly into our existing models, and that is precisely what makes them so valuable. They are telling us that the universe is more complex, more interesting, more surprising than our current theories allow. And that means there is more to learn, more to discover, more to understand. Science progresses, not just through confirmation, but through surprises, through anomalies that do not fit the existing framework. These anomalies force scientists to reconsider their assumptions, to modify their theories, sometimes even to abandon entire frameworks and build new ones from scratch. The history of astronomy is filled with such revolutions. The discovery that Earth orbits the Sun, not the other way around. The realization that the Milky Way is just one galaxy among many. The observation that the universe is expanding. The detection of dark matter and dark energy. Each of these discoveries initially seemed to contradict what astronomers believed, but each ultimately led to a deeper, more accurate understanding of the cosmos. Webb's discoveries of mature galaxies in the early universe may represent another such revolution, forcing us to rethink how galaxies form and evolve. One of the most unexpected and exciting aspects of Webb's observations is its ability to witness galaxies in the act of colliding and merging. In the modern universe, galaxy mergers are relatively rare events, occurring over hundreds of millions of years, but in the early universe, they were common. Matter was more densely packed, and galaxies had not yet spread as far apart as they are today. This meant that encounters were frequent, violent, and transformative. When two galaxies collide, their stars rarely crash into one another. Space is so vast that even in a galaxy packed with billions of suns, the distances between stars are immense. Instead, it is the gas clouds within galaxies that interact. Shock waves ripple through the gas, compressing it and triggering bursts of star formation where gas has been squeezed into stellar nurseries. These are not catastrophes, but engines of creation, the way the cosmos constructed its greatest structures. The revelation that such mergers were widespread so early challenges our expectations. Once again, galaxies did not wait billions of years to assemble. They were colliding and combining from the beginning, creating structures far more extensive and intricate than we anticipated. This rapid assembly may help explain why Webb observes massive galaxies so soon after the Big Bang. Galaxy mergers are not gentle events. Even though stars do not physically collide, the gravitational forces involved are enormous. Stars can be flung out of their galaxies entirely, cast into intergalactic space, where they will wander alone for eternity. Gas clouds can be heated to millions of degrees, glowing in X-rays. Supermassive black holes at the centers of the merging galaxies can spiral toward each other, eventually colliding in a cataclysmic event that sends ripples through space-time itself, gravitational waves that we can now detect with instruments like LIGO. The merged galaxy that results from such a collision will look completely different from either of its progenitors. Two spiral galaxies colliding typically produce an elliptical galaxy, a smooth, featureless blob with no spiral arms or disk structure. The merger scrambles the orbits of stars, erasing the organized rotation of the original galaxies and replacing it with random motion. The central black holes merge into a single, even more massive black hole. And the burst of star formation triggered by the collision can produce millions of new stars in a relatively short time, lighting up the merged galaxy in a brilliant blaze of stellar birth. When galaxies collide, they do so in slow motion by human standards, but quickly by cosmic ones. A typical merger takes hundreds of millions of years from first approach to final coalescence. During this time, the galaxies experience multiple passes, approaching, passing through each other, separating, then approaching again, gradually losing orbital energy to gravitational interactions until they finally merge completely. Each pass strips away gas and stars, creating long tidal tails that stream out into intergalactic space. These tails can be hundreds of thousands of light-years long, thin streams of stars and gas marking the paths the galaxies took. Sometimes, knots of matter in these tails can collapse under their own gravity, forming new dwarf galaxies, offspring of the collision. Observations of nearby merging galaxies show all stages of this process, from early encounters to final mergers, providing a timeline of what happens when galaxies collide. The history of our own Milky Way is inscribed in this process, Our galaxy likely arose from dozens, perhaps hundreds of smaller ones. Its stars hold the chemical signatures of these predecessors, each merger leaving an imprint in the distribution of elements and stellar paths. By studying early mergers with Webb, astronomers are piecing together not only cosmic history, but our personal galactic ancestry. There is elegance in this violence. From the chaos of collisions arose stability, from shattered pieces arose order. Every majestic spiral, every giant elliptical, every cluster of galaxies originated as a swarm of tiny sparks drawn together. Webb reveals the process unfolding, reminding us that destruction and creation are often two faces of the same cosmic transformation. To witness these merging galaxies is to observe the universe constructing itself. The small became immense, the simple became intricate. And in their light, we see the pattern of our own home written across the vastness of duration. Astronomers can even trace specific merger events in the Milky Way's past. The stars in our galaxy do not all move in neat, circular orbits around the center. Some have highly elliptical orbits, diving through the galactic disk at odd angles. These stars are likely remnants of smaller galaxies that merged with the Milky Way billions of years ago. Their unusual orbits are fossils of those ancient collisions, preserved in their motion. By mapping the positions and velocities of millions of stars, astronomers can identify streams and clusters that share similar orbital properties, suggesting they all originated in the same dwarf galaxy that was torn apart by the Milky Way's gravity. One such structure, called the Sagittarius Stream, is the remnant of a dwarf galaxy currently being consumed by our galaxy. Its stars are stretched in a thin stream that wraps around the Milky Way multiple times, like a river flowing through space. In a few billion years, these stars will be fully incorporated into our galaxy, and the Sagittarius dwarf will cease to exist as a separate entity. It will have become part of us. Another merger is scheduled for the distant future. The Andromeda Galaxy, our nearest large galactic neighbor, is currently moving toward us at about 120 kilometers per second. In approximately 4 billion years, Andromeda and the Milky Way will collide. Computer simulations show what this merger will look like from Earth, assuming Earth still exists. The night sky will be dominated by Andromeda, growing larger year by year until it fills much of the sky. The two galaxies will pass through each other, their spiral arms torn apart by tidal forces, creating spectacular streams of stars. They will separate, then approach again for a second pass, and possibly a third, each time losing energy until finally they merge completely into a single giant elliptical galaxy, sometimes called Milkomeda. The Sun and Earth, if they have survived, will likely be flung into a different part of this new galaxy, possibly into the halo, far from the center. But the collision itself poses no direct danger to our solar system. The distances between stars are so vast that the Sun will almost certainly not collide with any star from Andromeda. We will simply find ourselves in a different cosmic neighborhood. The universe is not arbitrary. Though galaxies appear scattered across the night, they are woven into an immense design, the cosmic web. Vast filaments of dark matter and gas extend for hundreds of millions of light years, linking clusters of galaxies like beads on a thread. Between these filaments stretch enormous voids, regions nearly devoid of matter. Together, they form the largest structure in existence, a cosmic skeleton upon which the universe is constructed. This web started taking shape during the cosmic dawn. As matter collapsed into the invisible framework of dark matter, gas flowed along filaments, nourishing the growth of galaxies and clusters. The first stars and galaxies were not isolated, they were nodes in this emerging network. To understand how the universe evolved, we must see not only galaxies themselves, but also the threads that connect them. the cosmic web emerged from tiny quantum fluctuations in the early universe. In the first moments after the Big Bang, space was almost perfectly smooth, but not quite. Tiny variations in density, differences of only 1 part in 100,000, existed at random. These fluctuations were stretched to cosmic scales by inflation, the brief period of exponential expansion that occurred in the first fraction of a second. Once inflation ended, these density variations began to grow under the influence of gravity. Slightly denser regions attracted more matter, becoming denser still. Slightly less dense regions lost matter, becoming emptier. Over hundreds of millions of years, this process amplified the initial tiny variations into the large-scale structure we see today. The densest regions became clusters of galaxies, the least dense became voids. And connecting them are the filaments, highways of matter flowing from voids toward clusters. The cosmic web is hierarchical, with structure on many scales. Small filaments connect individual galaxies into groups. Larger filaments connect groups into clusters. Still larger filaments connect clusters into superclusters. And the largest filaments span hundreds of millions of light years, connecting superclusters into the largest structures known. The pattern repeats at every scale, a fractal-like organization that reflects the universal action of gravity on the initial density fluctuations. In the voids, matter is sparse, with densities perhaps 10% of the cosmic average. In the filaments, densities are a few times the average. And in the clusters, where filaments intersect, densities can be hundreds or even thousands of times the average. With hundreds or thousands of galaxies packed into volumes just a few million light years across. Until recently, these filaments were nearly impossible to observe directly. Their gas is diffuse and dim, glowing only in the faint light of hydrogen. But Webb's extraordinary sensitivity in the infrared has begun to change that. By capturing the subtle signatures of distant galaxies aligned along filaments, Webb offers indirect glimpses of the web in its infancy. Patterns of clustering, shapes of protoclusters, and alignments of galaxies hint at the strands of structure stretching across space. Some of Webb's deep field images already suggest the presence of elongated groups of galaxies, the embryonic filaments of the cosmic web. These alignments are not coincidental. They are the fingerprints of gravity guiding matter into highways that would later develop into colossal structures. By mapping them, astronomers can compare reality with simulations, testing our understanding of dark matter and cosmic evolution. Computer simulations of the cosmic web are astonishingly detailed. By starting with the initial conditions of the early universe and applying the laws of gravity and gas dynamics, supercomputers can evolve the universe forward in time, showing how structure forms and grows. These simulations produce cosmic webs that look remarkably similar to the real universe, with filaments, clusters, and voids distributed in similar patterns. This agreement between simulation and observation is strong evidence that we understand the basic physics governing cosmic structure formation. But Webb is now providing observations of the web at such early times that they can test these simulations in new ways. If the simulations match Webb's observations of early protoclusters and filaments, it confirms our theories. If they do not, it tells us that something in our models, perhaps the properties of dark matter, perhaps the initial conditions, perhaps the physics of star formation, needs to be revised. The simulations require enormous computational resources. Modern cosmological simulations track billions of particles representing dark matter, along with gas dynamics, star formation, black hole growth, and feedback processes where energy from stars and black holes affects surrounding gas. The largest simulations use supercomputers with thousands of processors working in parallel, running for months to complete a single simulation of the universe from the Big Bang to the present. These simulations produce vast datasets, often petabytes in size, that must be analyzed using sophisticated software. Despite the computational challenges, these simulations have become essential tools for understanding cosmic structure formation. They allow astronomers to explore scenarios that cannot be observed directly, such as the distribution of dark matter or the evolution of the universe in regions beyond our observable horizon. The cosmic web is more than a framework. It is a circulatory system, channeling gas into galaxies and fueling star formation. Without these flows, galaxies would starve, their light dimming. With them, galaxies thrive, growing brighter and richer in stars. To study the web is to study the lifelines of the cosmos itself. For us, the implications are staggering. Our own Milky Way resides in one of these filaments, part of a vast structure known as the Laniakea supercluster. The stars above us, the atoms within us, all trace their origins to this interconnected network. Webb, by revealing the faint outlines of the web's first threads, is showing us the blueprint of our cosmic home. In the delicate glow of galaxies stretched across billions of light years, we glimpse the hidden architecture of creation. The cosmic web is the bridge between the chaos of the Big Bang and the order of the modern universe, a bridge that Webb is finally allowing us to see. The Laniakea supercluster, our cosmic address, is itself just one node in an even larger structure. Beyond Laniakea lie other superclusters, and beyond them, the largest structures known, vast walls and sheets of galaxies stretching across 1 billion light-years. The universe at the largest scales resembles a foam or sponge, with dense filaments and walls surrounding empty voids. This pattern repeats at every scale we can observe, from clusters of a few dozen galaxies up to structures encompassing hundreds of thousands. It is the natural outcome of gravity acting on the initial tiny density variations from the early universe. And remarkably, we can see this structure forming in Webb's images of the cosmic dawn, watching the first hints of organization emerge from primordial chaos. Laniakea, whose name means immeasurable heaven in Hawaiian, was only identified in 2014 through detailed mapping of galaxy velocities. It spans 500 million light-years and contains 100,000 galaxies, including our own Milky Way, but even Laniakea is not isolated. It is connected to other superclusters through filaments of the cosmic web. And all of these structures are moving together, flowing toward an even larger concentration of mass called the Great Attractor, whose nature is still not fully understood. The universe is a dynamic place, with galaxies and clusters in constant motion, guided by the gravitational pull of visible and dark matter distributed throughout space. To peer into the cosmic dawn is not just to study the past, it is to confront the question of origins, not only of galaxies and stars, but of ourselves. Every atom of calcium in our bones, every drop of oxygen in our lungs, every spark of iron in our blood was forged in the fiery deaths of ancient stars. When Webb captures the faint light of those first galaxies, it is revealing the very furnaces that made us possible. This knowledge transforms perspective. For centuries, humanity saw itself as separate from the heavens, gazing upward at stars as distant, unreachable lights. Now we understand they are family. Their chemistry flows through us. Their history is our history. By watching the universe awaken, we are watching our own beginning written across time and space. The elements that make up your body have extraordinary biographies. The hydrogen in your water molecules is primordial, formed in the Big Bang itself, 13.8 billion years old, as ancient as time. The carbon in your cells, the backbone of all organic molecules, was forged in the cores of massive stars through a delicate process called the triple alpha reaction, where 3 helium nuclei fuse to form carbon. The calcium in your bones, the iron in your blood, the zinc in your enzymes, all were created in the final moments of dying stars, either in the slow fusion of elements in stellar cores or in the explosive nucleosynthesis of supernovae. The gold in any jewelry you might wear was formed in the collision of two neutron stars, an event so violent it produces heavy elements that normal supernovae cannot create. Every element heavier than hydrogen has been through at least one star, and many have cycled through multiple generations of stars, each time being incorporated into new structures, new combinations, new forms. You are, quite literally, made of star stuff, assembled from atoms that have journeyed across the galaxy for billions of years. The emotional weight of this realization is profound. To see galaxies forming when the universe was only a few 100 million years old is to see the first brushstrokes of a cosmic masterpiece. It is to realize that creation was not a singular moment but an unfolding process, one that continues even now. Galaxies still collide and merge. Stars are still born and die. The story that began in the cosmic dawn continues in every sunrise here on Earth. Webb has made this story visible. Its golden mirrors gather particles of light that departed their sources before our planet existed, before the Earth itself had coalesced from dust. That light traveled across billions of years to meet us. Now, a silent message from the dawn. We are the first generation capable of reading it, of turning ancient radiation into knowledge and meaning, and in doing so, we are reminded of our fragility. Against the scale of billions of light years, our lives are brief. Against the scale of cosmic time, our civilizations are young. Yet the fact that we can look back so far, that we can reconstruct events at the edge of time, is itself extraordinary. It means that the universe has grown not only galaxies and stars, but minds capable of wondering where they came from. Consider the improbability of your existence. For you to be here, reading these words, countless events had to unfold in precisely the right way. The Big Bang had to occur with exactly the right properties for matter to form and structure to grow. The first stars had to forge heavy elements and scatter them through space. Our galaxy had to assemble from smaller fragments. Our sun had to form in a region with enough heavy elements to build rocky planets. Earth had to form at the right distance from the sun for liquid water to exist. Life had to emerge from chemistry and evolve for billions of years. Your ancestors, stretching back through countless generations, all had to survive long enough to reproduce. Every step of this chain, from the quantum fluctuations in the early universe to the specific sequence of events that led to your birth, was necessary. Break any link and you would not exist. In this sense, your existence is a miracle, not in the supernatural sense, but in the sense of being extraordinarily, almost impossibly improbable, and yet undeniably real. The chain of causation stretches back unbroken to the beginning of time. You exist because your parents existed, who existed because their parents existed, and so on back through thousands of generations of humans. But before humans came other species, other forms of life, stretching back through millions and billions of years of evolution to the first simple cells. And those cells arose from chemistry, complex organic molecules that assembled themselves from simpler compounds. And those compounds formed from elements scattered by dying stars. And those stars formed from hydrogen and helium produced in the Big Bang. There is a direct line of causation connecting you to the origin of the universe itself. You are not separate from the cosmos. You are the cosmos, a small part of it that has become aware of itself, capable of looking back across time and understanding its own history. The cosmic dawn is not only an era in history, it is a mirror. It reflects the possibility that intelligence was always seeded in the stars, waiting for matter to arrange itself into beings who could ask questions. When Webb shows us the first galaxies, it shows us not something foreign but something deeply familiar. It shows us home at the scale of the universe. The universe began in darkness, a silent expanse of hydrogen and helium, adrift in endless night. From that stillness came the first spark, stars that blazed, galaxies that grew, light that spread. Webb has given us a way to witness this transformation, to see the moment when the cosmos awoke. In those ancient furnaces, the raw materials of life were forged. In those first galaxies, the blueprint of the modern universe was drawn. Every planet, every ocean, every living creature traces its ancestry back to that dawn. To study, it is not to look at something far away. It is to look at the roots of who we are. This is why the cosmic dawn matters. It is not only a scientific milestone, but a human story. It tells us that creation is not finished, that the universe is still unfolding, still building, still alive. And it invites us to see ourselves as part of that story, brief in years, but eternal in origin. So, as Webb continues its silent watch, gathering light that has traveled across 13 billion years, we are left with a question. If the cosmos has already given rise to us, what else might it hold? What other dawns? What other stories are waiting in the dark? The question of other intelligent life in the universe becomes more poignant when we understand cosmic history. If galaxies formed quickly, if stars began creating heavy elements early, then Earth-like planets could have existed for billions of years before our own Earth formed. Life might have emerged on countless worlds throughout cosmic time. Some of those civilizations might be billions of years older than ours, having had time to spread across their galaxies, perhaps even to build structures we could detect. The fact that we have not yet found evidence of such civilizations is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The silence might mean that life is rare, or that intelligence is rare, or that civilizations tend not to last long enough to spread through space. Or perhaps we are simply looking in the wrong places, or listening for the wrong signals, and the galaxy is actually teeming with life we have not yet learned to recognize. The Drake equation attempts to quantify the number of communicating civilizations in our galaxy by multiplying factors like the rate of star formation, the fraction of stars with planets, the fraction of planets where life emerges, the fraction where intelligence evolves, and so on. Depending on the values assigned to these uncertain parameters, the equation can predict anywhere from 0 to millions of civilizations. We simply do not know. The discovery of thousands of exoplanets has shown that planets are common. Many stars have them. And some of those planets orbit in the habitable zone where liquid water could exist. But we do not yet know how common life itself is, how easily it arises from chemistry, or how often it evolves into intelligence capable of building civilizations. Webb's ability to analyze exoplanet atmospheres may begin to answer some of these questions by detecting biosignatures, combinations of gases like oxygen and methane that might indicate biological activity. The search continues. The light is still arriving, and the universe still has secrets to share. Thank you for joining me on this journey into the first chapter of time. The next chapters are waiting, and together we will keep reading the stars. Every night, the sky offers an invitation to look up, to wonder, to remember that we are part of something vast and ancient. The stars above us are not decorations but windows, openings through which we can glimpse the history of everything. In their light, we find not just distant suns, but our own origins, our connections to the cosmos, our place in the grand unfolding of existence. As Webb continues to explore the universe, as new telescopes come online, as our understanding deepens, we will continue this journey of discovery. And perhaps, somewhere among those distant galaxies, in the light of those ancient stars, we will find not just the history of the universe, but hints of our future, and maybe even companions in the cosmic adventure. Until then, we have the night sky, the gift of curiosity, and the light of distant galaxies still traveling toward us, carrying their ancient messages across the void. The universe is speaking, we are learning to listen, and the conversation has only just begun. The future of astronomy is bright. New instruments are being planned and built that will surpass even Webb's capabilities. Ground-based telescopes with mirrors 30 or even 40 meters across are under construction, able to gather more light than any previous instrument. Future space telescopes, optimized for different wavelengths, will complement Webb's infrared vision, observing in the ultraviolet, X-ray, and other regions of the spectrum. Gravitational wave detectors will map the collisions of black holes and neutron stars across cosmic time. And perhaps most excitingly, the next generation of extremely large telescopes may be capable of directly imaging exoplanets, taking actual photographs of worlds orbiting other stars and analyzing their atmospheres in detail to search for signs of life. We stand at a unique moment in human history. For the first time, we have the technology to peer back to the cosmic dawn and see the universe in its infancy. For the first time, we can detect and study thousands of planets around other stars. For the first time, we can map the large-scale structure of the universe and test our theories of cosmic evolution with precision. The questions we are asking now would have seemed like pure fantasy just a few generations ago. How did the first galaxies form? What are exoplanet atmospheres made of? Are we alone in the universe? These questions are no longer philosophical speculation. They are scientific inquiries, answerable through observation and experiment. And so the journey continues. Each observation adds another piece to the cosmic puzzle. Each discovery raises new questions. Each question drives us to look deeper, to build better instruments, to refine our theories. We are explorers, mapping the universe one photon at a time, assembling a picture of the cosmos that grows richer and more detailed with every passing year. The universe has been telling its story for nearly 14 billion years. We have only recently learned to listen. And the story, it turns out, is more magnificent than we ever imagined. The light is still arriving, the discoveries are still unfolding, and the universe, patient and eternal, waits for us to continue reading. The stars are calling, and we are answering.